Hello and welcome. Let's talk about drawing of resonance structures. Usually we draw resonance structures in chemistry. I'm Prof. Mo. How do we draw resonance structures? Resonance is just to go back and forth, up and down, left, right. And in structures, Lewis structures, Kekel structures, resonances usually represent representative molecules that interconvert into each other by relocation of pi bonds or electrons or charges. We will need to calculate formal charges during this process. We use a double-ended arrow to represent resonance. This is not equilibrium. Equilibrium will be half-barbed arrows. Okay, you can see an example here. That's a resonance arrow. Let's look at an example of the anion of a carbonate. You have two negatives because if you look closely, you see that we have two negative charges, right, on this oxygen. So let me call this A, B, and C. If I am to move electrons next to a double bond, I'll start from the lone pair. You move it inward, and then this double bond has a sigma bond, it has a pi. It's the pi bond that gives way. Remember again, the bond is made of two electrons. The reason why you have to open up the pi bond is this. There's a carbon there. So if you make a double bond between oxygen A and the carbon, and you keep the other double bond and you keep this bond, this carbon right here has 5 bonds around it. Those are 10 electrons, and that would be a felony. You don't want to do that. That's an organic felony. Someone needs to be jailed. So what we want to do is to make a double bond and open up the pi bond. Those 2 electrons will go to oxygen C. So if you're making a bond between oxygen A and the carbon, this is what you'll form. And then the pi bond opens up goes to oxygen C. That is oxygen C. Now oxygen C will have 6 electrons on it. If you do a formal charge calculation, oxygen has a valency of 6. It's in main group 6 of the periodic table. And then you can see it has 6 non-bonding electrons. And then you can see that it's bonded to one bond. Do the math, you're going to get -1. That accounts for the negative charge. Oxygen B right here is not affected, so it stays the way it was. But now you use the 2 electrons from oxygen A, so you're left with 4. And if you try to do the formal charge calculations on oxygen A, it will be again valency of 6 of oxygen minus 4 non-bonding and then 2 bonds, you get 0. There's no more negative. So that's why I say you have to account for the charges each time you do resonances. If I want to get the one here, if I want to get this, then I'll probably want to start from here, making a double bond, which happens to be this bond, and then again the pi bond has to open up. How do I know which is the pi bond? Come on, it has to be one of those two. One is pi, one is sigma. And then you'll end up with this structure. Ignore the arrows as drawn. You'll see again that this will be negative. Going with this formal charge calculations, you'll find the charge to be negative. And then going with the formal charge calculations, you find this oxygen to be 0. And if you want to go back to where you started, it's quite simple. You'll want to take this back in, and then the pi bond is going to be given back to this oxygen. You will get back this structure. See, they are all resonating, all interconverting amongst themselves. For everything we do in chemistry, most likely you're going to get a rule. Only pi bonds are the ones that are going to move, and non-bonding electrons. The non-bonding electrons in this case, we are talking about lone pair of electrons. They relocate to make a new bond. Okay? And then you do not want to change the number of paired and unpaired electrons. They must stay the same. the total number of paired and unpaired electrons must stay the same. And then you always want to move electrons towards the positive charge or towards a pi bond. This is what we just did. We did have an oxygen, and that oxygen was on a carbon, and the carbon had a double bond to another oxygen. I had called this A, I had called that C. So you can imagine that if I want to move this, I'll move it towards a double bond as this gives way. And I told you it's a pi bond that gives way. That's what this is saying, or towards a pi bond, towards an sp2 hybridized element. This carbon right here is sp2. Sometimes that element could be sp. Depends. Now, what this is saying, always move towards a positive charge, is because of this. Let's say you had a double bond to a carbon, and that carbon is bonded to a positive charged carbon. In this case, I want to move electrons towards the positive charge that way. Okay, and you realize that now my CH2 will have a double bond, and then I'm maintaining my octet state, and then this other CH2 on the right will have a plus charge because it lost one valent electron as the double bond relocated. If you doubt, you do your formal charge calculations of this carbon. Carbon has a valency of 4, so it will be 4 minus how many bonds? There's 2 hydrogens and a single bond here, 3. There's no lone pair, you see. It becomes plus 1, which accounts for that. That's called an allylic carbocation. Rule number 4, always preserve the octet rule. And that's what I'm trying to do, especially here. If I'm moving a double bond this way, I don't want to keep the other double bond. One has to give way to maintain 8 electrons around that carbon. Except for elements like hydrogens, which are just happy with 2 electrons on them. And also unlike sulfur, which can take more than 8, because remember, in the Lewis structure of sulfuric acid, for example, the sulfur itself is surrounded by 12 electrons. There are exceptions, but for most of the part, we want to maintain the octet rule. Let me show you more examples. So what about the nitrate ion? If you want to show the resonance structures of nitrate and ion, just draw one of them to begin with, and then choose which part you're going to start with. Again, I have a lone pair. According to our steps, we said if you have a lone pair on an element next to a double bond, you want to start from the lone pair. You're making a double bond here, and to preserve octet state, you want the pi bond next door to move over. So you made a double bond right here, and the lone pair of the pi bond went over. Again, you don't stop there. You want to do the formal charges. Again, for purposes of explanation, let's label those A, B, C. So what I'll do, I will find the formal charge of A and C, because those are the ones that did the resonance. So formal charge of the formal charge of the nitrogen will be, so nitrogen in this case is in main group 5, and then it has no lone pair, it's already octet, and then it has 4 bonds on it, so it stays plus 1, so I need to put plus 1 here. And then for this oxygen, formal charge of the oxygen is in main group 6. There are 4 non-bonding electrons, and then there are 2 bonds. If you subtract, you get a 0, so no charge on this oxygen. For oxygen C, the formal charge will be equal to main valency of oxygen, which is 6, minus non-bonding electrons 1, 2, 3, 4, 5, 6, minus number of bond left is 1, so I get negative 1. That was a negative. We did not touch B. B stays negative. Okay, and then we can do the next resonance, get the next resonance structure, where in this case See, the double bond was here, now it's on A, we want to put it on B, so I'll have to push this way, make a double bond in there, and then open one of the bonds. So opening one of the bonds, I get a lone pair, and then the bond landed right here to make a double bond. So again, if you do the formal charge, the formal charge of that oxygen will be 0, the formal charge of this will be negative, the formal charge will be negative, just as we did right here. These are the three formal charges. These are the three resonance contributing structures of a nitrate. Which one is most favored? None of them, because they are equal. They are equal in stability. We'll discuss that in a different lesson. However, you can see that the negative charge moved over from ABC, or to ABC, you know. So we are saying that that negative charge is trailing this way through those bonds. So this structure right here, we call it a hybrid, which is just an average of all these. This is a hybrid resonance structure with those dotted lines showing the traction where the negative charge followed. Okay. For the allylic cation, if you're starting with this time I have a double bond and a positive charge, only one arrow applies. Here, lone pair next to a double bond, you'll always be moving 2 per arrow pushing. So we are pushing towards the positive charge according to our rule that we learned before. And this carbon right here will be one bond less, okay, because we're moving the double bond right here. Using this double-ended arrow, we are saying we are moving 2 electrons, okay, 2 electron movement. And now you'll see that this carbon right here that had a plus charge before will have no formal charge, because that carbon has a valency of 4 in the periodic table. It's found in the fourth main group of the periodic table. There's no lone pair and there is 4 bonds around it. Same will apply for this other one. So these 2 carbons will have similar formal charge of 0. But now when you look at the last one, this one, there's no lone pair. Formal charge will be equal to 4 minus. There's no lone pair, yet there's 1, 2, 3 bonds. The answer is +1. So we need to put a plus charge here. So you can see we move the positive charge over to the other side of the molecule, and the pi bond also moved. These are the only 2 resonance structures of the cation. If you want to draw the hybrid, it's similar as explained before. We are just tracking how the positive charge went. It went between these 3 elements, right? If you could call 1, 2, and 3, it went between those 3. So we draw the dashed lines showing, illustrating, suggesting the traction, the path of the positive charge. And we're calling it partial because it's moving, bouncing back and forth. It's partial, it's not full positive along those 3 elements. It never goes to the last carbon. You see, this last carbon right here never gets the plus charge. So our traction doesn't go all the way to the end. That's the hybrid, the average of the resonance complexes. That was a cation. Remember, cation is whenever you have a positive charge. Okay, what is the resonance of an allylic anion? Allylic anion. Anions are negatively charged species. Allylic because you have a charge on an element next to a double bond. Charge on an element next to a double bond. We call that allylic for carbon systems. So again, I have my resonance arrow drawn right there. We start off with this system. Since I have a double bond next to an element with a lone pair, I want to start from the lone pair, dropping it right there, and then dropping the pi bond electrons onto the carbon over. We want to give way. Carbon must be octet. There's an implied hydrogen there. Okay, you must have learned about how to draw organic structures in an earlier lesson. So you're making a double bond and this gives way. Okay, so the double bond is formed there, and then the 2 electrons are landing on here. Again, if you look closely, the formal charge of this carbon changed to 0 from negative because the carbon has valency of 4. There's no lone pairs, it's octet already, 8 electrons around it. And then there's 4 bonds, you get 0. So this has a formal charge of 0. What about this? This will also have a formal charge of 0. What about the last one? For the last one, the formal charge equals again valency of carbon, neutral carbon atom on the periodic table is 4. And then we say that there's 2 electrons that are not bonded, they are lonely, they're in the lone pair, they are in the lone pair. And then you have 3 bonds, this bond to a carbon and 2 bonds to the hydrogens. So it's 3. If you subtract, you're going to get -1. So we need to show a negative formal charge on that. Like before with the allylic cation, we have to show the hybrid of the allylic anion, and these lines are just showing the pathway of the negative charge between in the 2 resonance structures. And I say partial negative because the negative charge is distributing itself as it moves around, as it bounces around, as it resonates, as it does resonance. Okay, how about if you're given a ring like this? This is called a phenoxide. Okay, for curiosity, if you're curious to know, that's a phenoxide anion because it's negatively charged. This one will tend to have more. So let's start again. It looks like an allylic system because we do have a lone pair next to a double bond. So I will push my electrons inward this way to make a double bond, which is this. And then the double bond next door has to give way to maintain 8 electrons on the central carbon. So those 2 electrons moving over those. Like as usual, we have to find the formal charges. So the formal charges on the oxygen, neutral oxygen has a valency of 6. You see that it has 6 electrons. You also see it's bonded to 1 bond, so it's -1. So that's why there's a negative here. But for this one, if you do the formal charge for the other oxygen, there's 4 electrons because you used 2 of them to make the pi bond, the purple line. Okay, 4 non-bonding electrons, and then there's 2 bonds to the oxygen. It becomes 0. No need to show any charge on there. For this carbon, there is an implied hydrogen. Like I said, by now you should have learnt how to draw organic structures, knowing that carbon must always have 4 bonds, and any bond that is quote unquote missing must be going to a hydrogen, just not drawn, it's implied. So that's why I know there's a hydrogen there. So if I'm to do the formal charge calculations onto this carbon, the formal charge will be carbon has a valency of 4, there's 2 non-bonding electrons, and then there's 3 bonds, you can see them. So it's -1. I need to show a negative on that carbon. So that is the second resonance structure. And then we go to the next one. So I'll have to drop it here, start from the lone pair, make a double bond next door, and then make way, give way, open up the pi bond. There's an implied hydrogen. There is an implied hydrogen. Okay, this one will end up having a valence, formal charge of 0 if you do the math. This one also has a valency of 0 if you do the math. But for this bottom one right here, this one right here, the formal charge will change from 0 to something. So let's determine. It will be Fc of that carbon will be 4 minus 2 non-bonding electrons, and you can see we have 3 bonds. The answer is -1. The negative charge comes there. We keep doing the same. Move this over and then open this over to the next element. Remember, there's an implied hydrogen there. I will show it. There's an implied hydrogen here. I will show it. So we are bouncing in here to make this double bond, and then we are opening this pi bond, so we no longer have it. If you do the formal charge on that carbon, it will be 4 valency of carbon minus 2 non-bonding electrons, 4 more charge, 4 minus 2 non-bonding electrons minus 3 bonds, so it's -1. That's why we have a negative on that carbon. And then if you do it one more time the allylic way, make a double bond and give back, you go back where you started from. So this phenoxide ion as drawn has 4 resonance structures. The last one is a repetition. If I'm to draw the hybrid, I'm just showing the traction on how the electrons flow around the ring. So they started off from the oxygen and they went all around the ring, touching every carbon possible. So that's the hybrid, and I'm showing partial negatives because it's a negative charge being distributed around the ring. Okay, I hope that helped. There are so many structures you can practice with out there to draw resonances, but the principle is the same. When you have a negative charge, a lone pair next to double bond, start from the lone pair, push 2 arrows. When it's a plus charge next to a double bond, just push once towards the plus charge. Be sure to do your formal charge calculations. I hope that helps.